Thank you so much, Maria Felice, for this wonderful organization today. Thank you for listening so relevant themes and topics. And I'm also happy to be after Joseph, because he discussed about corruption, and I will discuss a little bit about corruption. Basically, what I'm going to do now, I share my screen, is to describe a device I'm quite using a lot in my research activity, which is complex networks. And can you see my screen?
Yes, perfectly.
Okay, Control L. Okay. For frauds and corruption, and basically the point is that corruption and frauds are destabilizing events. It's something pertaining to the socioeconomic environment, and they are able to destabilize, to provide, let's say, a disruption of an overall framework in some sense. And there are systemic problems because they involve elements that are interconnected. They can be individuals or entities or institutions in many cases. Once you provide a macroscopic shock in these frameworks, then you see an aggregate fluctuation of the overall system. This means that basically it's not trivial to absorb something appearing in a very small part of the system, but sometimes it can provide, it can rise, it can lead to the disruption of the system itself. And in this context, complex networks are very relevant because they are able to describe systems with interconnected components. And so, in our point of view, they can be used for evaluating and modeling corruption and frauds. They represent the reality, everything. If you turn your view around, you will see a lot of systems with interconnected units, social networks, for example, but also international trade, or also the connection between friends or among friends or pairs when you deal with academicians, co-authorships. Everything is a network. So it's easier, I think, to see a network than not seeing it. And that's there are several definitions of units and interconnectedness. And starting from this point of view, you can easily deal with a complex network when you want to deal with a problem, but it's not always easy to find a solution of your problem. So easy to model, not always easy to find something to solve the problem you're dealing with. According to an analytical point of view, I'm trying to avoid math. I'm a mathematician as a background, but this is, I think, the only slide with some formulas. Basically, it's but I have to give you some information about the analytical formulation of the complex networks. Basically, we are dealing with graphs. Graphs is a couple of nodes and links. The links connect nodes. So this means that basically you can have a connection between two different nodes or not. If you have a connection, there is a link, otherwise there is not a link. And usually the graph is weighted in the sense that every link is associated with a positive real number describing the entity of such a link. And according to this definition, when this weight is 0, then this means that there is not a link. So this means that once you collect all these weights in a n-squared matrix W, through W, you are able to describe all the links of the network. In the case in which the weights can be 0 or 1, this means that basically when they are positive, they are only 1. This means that you are not weighting the links. So you are just stating that there is a link. And in this case, the network is unweighted. In other case, when there is not this binary condition on the weights, the network is weighted. Network can be directed or undirected. In the former case, there is not symmetry in the adjacency matrix. This means that I have arrows moving from a node to another. and the converse arrow cannot appear, maybe, or can be different, can have different weight. When there is not an arrow, but it is just a connection between two different nodes, then the adjacency matrix is symmetric, and this couple of nodes and the adjacency matrix is a network. So in the case of undirected network, according to our definition, I'm showing you the set of the nodes, 5 in this case, and the adjacency matrix filled by ones and zeros. I'm just presenting examples in the unweighted case, so not difficult to write some numbers instead of the ones. Look that the matrix W is symmetric. We have number 1 in the first row, second column, and accordingly also in the first column, second row. This means that the node 1 and 2 are connected. If I want to provide a graphical representation of this network, I need to deal with something like this one, describing the connection that you had in the adjacency matrix, and of course, listing also the nodes of the set B. The same set of the nodes in the directed case. Look here, we have in the first row, second column, a 1, but this one does not appear in the first column and second row. This means that there is an arrow moving from the node 1 to node 2, but the converse arrow does not appear. According to this weighted adjacency matrix, I have this situation easy for me when you have that all the arrows are going to a given node and no arrows are outgoing from this node. This means that this node is a sink. When there are only arrows moving from a node without any incoming arrow, this means that that node is a source. In the directed case, so you have also these two definitions. And this is the simplest way to view networks, but it's clear that there are a lot of different situations to describe networks. For example, we can imagine that nodes are classified into 2 or several categories, multipartite networks, sometimes you can have, bipartite when you have only 2 categories, and links can appear only between nodes of different categories. I present also some relevant contributions from the literature dealing with fraud, for example, in this case, and these types of frameworks. For example, in Tuminello et al. In 2023, the authors explored the insurance fraud detection by exploring the connections between subjects and accidents, or vehicles and accidents. It's clear that you have individuals and accidents, so only links between individuals and accidents, and this means that then there cannot be a link between 2 different accidents. You can project, of course, the network is a device that one can use in an efficient way. I will not present this point here, to connect also accident according to the point that they are associated to the same subject. And this is a projection method that can allow to describe network as before. So according to the definition I gave you before, also in this bipartite case, under a graphical point of view, we can imagine something like this when we have 2 different types of nodes, links only where links are appear only in between different nodes. In the multi-layer networks, we have that the same nodes. So we move from an identical set of the same one set of nodes, only one, and we have that these nodes have different attributes, and you can imagine that each attribute is associated with a layer. And you imagine that the nodes are linked within the same layer, but also under an interlayer point of view. And in this context, for example, we have this paper by Luna Ply and Nicolas Carlock in 2020, where the authors describe the corruption case in Mexico, very famous corruption case in Mexico, involving multi-networked shell companies. So under different points of view, they built a network involving always the same shell companies, but under different perspectives. And this is a graphical representation of multi-layer networks. You have different layers that you can imagine that there are plants, and arcs there are different in the different layers, and there are also interlayer arcs. In the weighted network cases, weights can be of different nature. So the definition is very straightforward. A weight is a number describing the relevance of the connection of between the considered nodes. And according to this simple definition, we have different criteria of connections. You can imagine, for example, to link individuals or entities according to their similarity. This means that the weight grows as the nodes are more similar in terms of a given variable. I don't know what. Correlation, sometimes you have that the strongest correlation. So if two nodes tend to behave more similarly, then they have a higher value of the weight. Or the impact. This is the case of directed networks. When you imagine that a node has an influence on another one, and so you set an arrow moving from the first node to the second one, weighted through the entity of such an influence, or simply the flow moving from a node to another, and the weight grows as the flow grows. Or otherwise, you can imagine your favorite way to connect the units. Everything is a network. Sometimes they are not so realistic, but for example, you can imagine to connect people having the names starting with the same letter. Okay, not bad at all. It's a network. I don't know how to treat it. I don't know what's the meaningfulness of such a network, but basically it's still a network. So very, very easy, intuitive to deal with weights. And for example, in this paper in Complexity by Zanin et al. About credit card fraud detection, the authors explored the illicit transactions in credit cards, and they have dealt with some features of such transactions. And the weights are driven by similarity of the considered couples of features, so between two different nodes, with a theoretically illicit value. According to this definition, they built a model and they explored this type of problem. In the network, a prominent role is played by the centrality measures. There are characteristics of the nodes. There are quantities associated to the description of the nodes. They are crucial for understanding the networks. They can allow us also to understand the interconnections, because sometimes you can you want also to deal with the contextualization or the propagation of a shock. And usually the nodal characteristics are local analysis, pertain to the local analysis of the network, while an overview of the entire network can be given by taking an average of the nodal characteristics of the network, so the nodal centrality measures. I show you some examples. For example, betweenness. Betweenness is, just briefly, the percentage of the shortest path, including a given node, in the overall network. This means that you take a couple of nodes and you consider the shortest path between these two nodes, so the trajectory that is the lowest one in terms of weights or in terms of number of links, and you point a value, a score 1, if there is a given node k, which is the one for which you want to describe the betweenness. And this quantity, this centrality measures emphasizes nodes that are relevant in disconnecting the network when they are removed. The betweenness does not deal with the relevance of the node within the network in terms of connections, but in terms of, let's say, flow from a side of the network to another one. I'll show you an example. For example, here, look at this red node in this network. Of course, it is not the most connected node in the overall network, but in terms of the betweenness, it is the most relevant one. because if you remove this node, then you obtain two different disconnected components of the network. So this is a crucial quantity in order to understand the link between two different sides of the same network. And in this paper, the betweenness is relevant in terms of the analysis of the criminal networks. This very beautiful paper by my friend Rosanna Grassi et al. In 2019, published in Social Networks, described the criminals under two different perspectives. They are the leaders and the collaborators of the leaders. So this lead to a bipartite network. And the point is that when you want to understand which is the most relevant criminal in a so strange network, you have to identify the one having a higher value of betweenness, because this is the individual that links more strongly several sides of this criminal world. So, and in this context, I didn't show you the paper and the results, but there was also some analysis of how Saddam Hussein was captured in Iraq, and that was for the presence of some betweenness, high betweenness of the nodes leading to Saddam Hussein. So that's very relevant. And these two papers are written with my colleague and friend and very dearest friend for me, an economist, Raffaella Coppier, in the University of Macerata, and published it several years ago. We speak about a shame cost. This means that basically we have a corruption-free like this one with an entrepreneur. This is an example of what we can have. The entrepreneur can evade taxes or not evade taxes. If after the first move of the entrepreneur, there is an inspector eye who can check or not check the evasion of the entrepreneur. If no evasion occurs, of course, the game ends without with the same equilibrium. And when there is an evasion, then if the inspector does not check the evasion, this means that the game ends. When she checks, then we imagine that entrepreneur and inspector can agree on a bribe and lead to a corruption. A bribe to avoid the reporting of the evasion. The bribe can be refused, of course. In that case, the evasion is reported and the game ends. Otherwise, the bribe can be accepted and can be stated, accepted, or declined. In any case, the game ends. So evasion and bribe are something probabilistic in many models, but basically what's the point? Why sometimes at an economic point of view, people avoid evading taxes or asking for a bribe? For the presence of the shame cost, of the social stigma in being detected in this illicit behavior. So social stigma, shame cost, it's something that we have hypothesized in our papers with Raffaella as an exogenous terms driving the motivation for leading to evasion or asking for a bribe. But it's clear that they pertain to the social network of these blue spots, which are entrepreneurs or inspectors, associated to the surrounding environment, and judging the behavior of entrepreneurs and the tax inspector in a strong way, maybe if there is a strong community around these nodes. So community, what does it mean, community? The community structure of a node can be represented still in the context of the network through the degree and the clustering coefficients. These are the most relevant centrality measures, nodal centrality measures that can capture this concept. For the degree is very simple. It counts the number of adjacencies of a given nodes. So a given node, and when the network is weighted, it is not longer the degree, it is called the strength, because the number of adjacencies is also weighted through the weights. and it emphasizes nodes having a lot of connections, the degree. When the degree is high, this means that the node has a lot of connections, and this means that the node is a hub. And for example, in this case, the red node has a degree 10. This means that it is a hub, and while all the others have degree 1. So this is an example of a star network, because it is similar to a star, and basically it points the attention to the relevance of the red node in having a strong community around him. For the clustering coefficient, let us start with a picture, unusually, and look at these two different networks here. And of course, point your attention to node I, which is the central one. Node I has degree 4 in both cases. But if I ask you, according to your intuition, which is the strongest community structure around I, I'm quite sure that everyone will say that on the left-hand side, we have a stronger community structure. And what's the difference between these two different networks? Well, the difference is that the adjacencies of I are all connected in the left-hand side of the network, while only some of them are connected in the right-hand side. Be reminded the possible number of triangles that can be built around I in a tridimensional network, because you have to imagine that this network is a tridimensional is 6. Also, the diagonals can be connected through these rounded arcs that you can see here. So in the left-hand side case, you have that all the 6 possible triangles around I appear, and this means that the ratio between the existing triangles over the the hypothetically existing one is 1 on the left-hand side, and it is 0.5 on the right-hand side, because in the right-hand side we have only 3 possible triangles around the 6 possible ones. So this is exactly the way in which the clustering coefficient works, in the sense that it counts the number of really existing triangles over the possibly existing ones. And so it emphasizes nodes having adjacencies that are strongly connected, so forming a strong community around that node. Basically, if you think at the friendship network, this means that all my friends are also friends one with the other, and this means that when I go out for dinner in the evening, I can let's say book a table for 20 people, and I will meet all my friends. In the case of a weak community structure, I need to go out 20 times for having a dinner with my friends, because they do not know one with the others. So this is a very, very clear example of strong community. And to conclude, the last relevant problem, according to my presentation today on complex networks for frauds and corruption, is the concept of resilience, which is very intuitive, is the ability of the network to absorb a shock. And the frauds are shocks in financial and economic systems. And indeed, we have evidence, and in the literature, this is one of the most recent papers I found on the resilience in banking systems against the fraud under machine learning procedure, okay? But basically, we are dealing with the resilience against fraud. So resilience means that, for example, in this context, you provide a shock to the network that can be, for example, a shock a microscopic shock, a shock in the node. So the node with the arrow, with the red arrow, will be shocked. And what can happen? We don't know, basically. Sometimes you have that the node is removed and all the arcs moving from this node are removed. This means that the network becomes disconnected, in this case with 4 connected components with an isolated node on the left side down. Okay. Or otherwise, you can have a weakening of the connections between the different nodes, or you can have a propagation of the shock, very strong at the beginning, and then still weaker as the distance from the shock and node increases. Or you can have the converse situation of the snowball case, in which you have a weak propagation of the shock at the beginning and a stronger propagation once the distance from the shocking node increases. So this is what basically I wanted to describe, to discuss with you today. Frauds and corruption involve interconnected agents, and there is evidence in the literature on the presence of complex networks for describing these types of problems. And the richness of the complex networks works under a methodological point of view, but also for application, is an opportunity to build models and obtain policy implications to contrast these two detrimental facts of the human society. And I thank you for your attention.